Okay. So last week we learned about the definition of continuity. So that a function is continuous at a point if the limit of the function is equal to the value of the function at that point. And we sorted three types of discontinuities and saw a bunch of examples. Now we will learn, sorry, a couple of basic theorems about continuity, and then we will continue. There are two options to continue to derivatives, or it's like goosebumps, עשו בעצמך in Hebrew. When you choose, you know, the story Goosebumps. I'm sure you choose that one.
The movie.
It's based on a
Jack
book.
Black.
And this one, right? What עשו בעצמך? Okay, dear readers, be careful, you're choosing one.
It's like the choose your own story. It's very like
Yeah, exactly. But
go to page.
it's a choose your own story horror book. Exactly, that was meant to be. Oh, the two choices was a lot. I needed to explain this joke for
Because
far
either way we're going to our doom.
far too long. Yeah, and we also like you go through all the different passages, right? Because we want to read the entire book. So we need to do derivatives and we need to talk about the trigonometric functions. Okay, the detour. So I will decide later what to start with.
So would you say the lesson flow would be continuous?
It would be not continuous, that's the point. Okay,
So we
so
wouldn't continue that. Said we were going to continue onto that. Not going to continue.
okay, we'll continue on continuously. Lecture 16. So a couple of things in any case. First, proposition. Assume f of x is oh, that's silly. I confused the theorem about derivative. So it won't be a couple of things, it would be one thing. Assume it does start the same. Assume the limit when x goes to x0 of f of x is y0, and assume g is continuous at y0. Then the limit as x approaches x0 or g of f of x, what do you think it would be?
The g of y0.
G of y0, exactly. Yes. That's so first of all, to put it in context, this is the special case of arithmetics of limits that we did not discuss with sequences. Why? Because this is composition and sequences does not have composition generally. So it's a new thing. We're saying we have a function within a function and we know the limit of the inner function. What can we say about composition? So in general, I skipped that. I usually do an example that in general, it's not true. I skip that. When the outer function is continuous, then the theorem actually holds. The composition, the limit of the composition is just as expected. And we need to prove that. before I will prove that, before proving that proposition, we will prove the following helpful lemma. And it's helpful not just for this proposition, but in general. Assume f of x is continuous at x0 and assume that an is some sequence that tends to x0. Then f of an, what will be the limit of f of an?
X0.
Not exactly. F of x0. And why does it follow from continuity? Because an is close to x0. Continuity says that close to x0, the y values are close to the actual y value at x0. But the proof has some twists and turns you should pay attention to. So I'll write the full proof. And after that, the proof of the proposition is really easy. That's the main thing from taken out from the proposition involved. So what is the proof of that level? First, by definition, since f of x is continuous at x0, what does it mean? What's the definition of continuity?
That the limit approaching x0 is equal to the limit of x0.
Yes. The value of the limit. The limit equals the value of the point. Okay. Tell me what next. What can we use here? We have an that approaches x0. And we know what the limit is when x approaches x0. So what can we do with these two? Why? What do we think about using? What's the definition of a limit of a function?
Up to,
What?
we have two.
Which one of them feels related to this theorem? Obviously. What the definition says, the limit when x goes to x0 of f of x is L. Let's call this L for a second. What does it tell us?
That opinions.
No, the limit of a function. Remember, the limit as x goes to x0 of some function, let's switch the name of the function altogether to h. It's L if, continue that sentence. When is the limit of a function L? Using Heine.
If for any sequence approaching x0,
Let's call it Bn. Approaching x0, yeah.
h of Bn is approaching now.
True, and h of Bn. Sorry, is approaching f. Does this sentence make sense to you?
Yeah.
So what can we say from what we have here? What can we plug in to f of x here?
Yeah, F of A.
F of a n, and it's ought to be the limit f of x 0, right? Okay. If it was only that easy, there is a mistake in that sentence. It's not actually true. It's close, but there is a mistake here. Who can spot the mistake?
H of n.
No. That makes sense. You take a sequence that's close to x0, you plug it into the function, and you get something that's close to L. It's not a small mistake, it's not a big mistake, but it's important.
Every sequence is different.
But it says for any every no no, that's not an English class. Any or every is the same for me.
Exist.
No, it's supposed to be every for every sequence. So if it's true for every sequence, we can plug in at an because it's one of every sequence. Yes, Sammy?
Bn doesn't equal x0.
Exactly. But Bn is not supposed to touch the actual point. And the reason that continuity fixes that, because when it's continuous, it doesn't matter if you reach the actual points, everything works fine. And the question is, how do we say that? Okay. But here we do not know if an equals x0. We will decompose it. Decompose, yeah, decompose. No, it's not decompose. Decompose is what you do after you die, right? I want to break it into two subsequences. Which word is
Yeah,
better?
decompose is.
It is. It
Yeah.
sounds.
Yeah.
Doesn't sound right.
No, when it's a sequence of numbers, I think
Split. Yes, we will split an into two sub sequences. First, k n, which is always different than x0, but still tends to x0. And the subsequence of all other elements, the complement, let's call it amn, which is the constant function x0, right? Because all of the elements that are not different from x0 are actually x0. So you have at most two subsequences. One of them is constantly x0, and the other one is never x0. Now, f of akn tends to f of x0 because that's by the very definition, by a Heine definition of a limit, because this is a sequence that is close to x0 but never actually reaches x0. That is what we are allowed to plug in into f. But what about f of amn, the other sequence? What is that? The other elements which are not of this sequence are all actually equals to x0. So what does that equal to? F of x0, exactly. So the only partial limit of f of an, because we took two subsequences that cover all, is f of x0, and therefore it is the limit. There is only one partial limit, and it's the limit, and then we finish the proof. Now, let's get back to proving the proposition. We assume that G is continuous at y0, and we assume the limit as x goes to x0 of f of x is y0. We assume that what we need to prove, we need to prove that the limit as x approaches x0 of g of f of x is g of y0. That was the claim, and now we need to prove it. So why is that true? Consider an arbitrary an that approaches x0 yet never reaches x0. Where should we plug it in? Not G. The limit you need to prove is G of f. So we need to prove that G of f of an approaches G of y0. Agreed? So now, but we do know what happens when we plug an into f. We know that f of an, what does that approach? An is close to x0. Therefore, by this limit here, if we plug in an instead of x, where does the y values tend to? y0. Right? We know that the limit of f is y0. If we plug in numbers close to x0, the y values would be close to y0. And since G is continuous at y0, by the lemma, we can apply it to both sides. Look at that's exactly the previous lemma. The previous lemma says that if f is continuous at x0, and we assume that an tends to x0, then we can apply f to both sides. Then f of an goes to f of x0. That's the lemma we proved. And the reason behind it, the main reason is we don't care if an actually reaches x0 or not, because f is continuous. Being close to x0 or actually plugging in x0 is the same thing, right? So we can, due to the continuity, or thanks to the continuity, we can say that g of f of an tends to g of y0 exactly as needed, and we are done. Yes, Thomas.
I wanted to ask, when you say G is continuous at y0, you mean x equals y0, right?
Yeah, that's what's confusing about composition always. Whoever was x-axis just a minute ago, or whoever was y-axis just a minute ago, now is the x-axis, right? Because y0 is the y-axis of f, and it's the x-axis of G. Yeah. So, but in any case, if you think about your question, the answer is obvious because G is some function, and I'm telling you it's continuous at some number. The fact that I chose to call it y0 is irrelevant. It could be 3. G is continuous at 3. So it always says when x tends to 3. We never talk about continuity in the y value. It makes no sense. Any questions so far? Okay, I'm making sure I didn't forget anything about that chapter. Calc 1. And then I'm moving on. I think we'll do trigonometry. We had enough suffering today with the linear. Let's do something easy with calculus. Yes. The only thing I did not do, but I didn't plan to do, is talking about the continuity of the inverse function. We assume that the inverse function of a continuous function is a continuous function. Whoever wish to see the proof is more than welcome to look at that video. But for a long time, I'm not doing it during lectures because it's too much discrete mathematics along with calculus, and no one follows it usually. And also there are more important things I wish to go over. The derivative. I wonder when in the general order of the course I usually do the trigonometric function. Oh, it's surprising to me.
Of yourself.
Yes, that's me holding me.
Where did you get that from?
And it was custom made, not generally sold.
How much?
And what? I think somewhere in the lines of 1,000 shekels, but it wasn't like a birthday. It was a birthday. No, it wasn't a birthday of me. To pin stick pins in. Yeah. It was a birthday gift by my wife. Yeah, I did the trigonometric functions before continuity in general. I don't know why. Whatever. Okay. So now a teacher, now a fun teacher, and to trigonometric function. And a question, a historic question: when were the trigonometric functions invented?
Around the Pythagorean period.
So did Euclides use trigonometric functions?
Oh,
No.
He might have written it like, no.
Yeah, so the whole way of thinking about function is much more modern. I'm not actually sure what's the answer to the question, when does sine and cosine were invented. I looked it up. I don't remember something spectacular. But yeah, Euclid did speak about it, but not in terms of function. Euclid spoke, and he didn't speak directly about the trigonometric functions. He spoke about a thing called the arc. What is the arc? No, I think it's not the arc. I forgot the name. I think it's the
Cosecant?
no.
is it part of
First
the-
of all, metal in Hebrew, that's the first word I forgot. Metal. What do you call the line, the segment between 2 points? Does it have a name?
Yeah, what part? Like that line
The
over
line,
there.
that line.
That line.
In Hebrew, we call it metal. It's the line between 2
I think
points on the graph.
it's either a segment or a section.
It's not a
Oh,
string.
between 2
that's
points
for
on a
sure.
graph or the
Yeah,
circle.
on a graph in general. It doesn't really matter. I think there is a name for it. I forgot it. But that he did speak of. I also forgot the name. I'm not sure if we wrote it anywhere. Let me just make sure for a second because it drives me crazy. Did I write it anywhere? If I did, it will be in the Shara lectures. Chord. Chord. First of all, chord is the
yeah,
way.
Yeah.
Yeah, and it's the chord function. I did write it. Yeah, quite probably. Yes, wow, with the proof. Okay, I'm happy with myself. Euclid did speak about the chord function, which is the length. It wasn't function. He talked about the length of a chord, which is the segment between 2 points on a circle specifically, but chord in general could be between that. And one can calculate that the chord is actually 2 times sine of x over 2. So it's nearly sine. So it really almost talked about sine, but very, very differently than the way we talk about it more generally today. Okay. Nice. Okay. I won't write any of it up, but it was a general knowledge question. Okay. Euclid did everything first. So we wish to define sine of x and cosine of x. For your best recollection, what is the definition of sine of x and cosine of x? Yes. SOHCAHTOA. Yes.
Opposite over hypotenuse.
Yeah. SOHCAHTOA. Well,
Wow, I can't believe they learn this in other places.
they don't.
Wow.
They don't.
You don't learn this in Israel?
No, the reason I know it is because I teach. I'm having some mistake here. I'll make sure in a second what the mistake is. But when I taught international students from America, they told me. So it's a sine is first of all, it's age.
Yeah.
That's it. Yeah, I think that.
No, they get rid of the H at the end.
Yeah, let's SOHCAHTOA. Okay, I think you're right, but sine is opposite over the hypotenuse. Cosine is adjacent over the no.
H, there's an H there.
SOHCA,
Yeah.
over the hypotenuse, and tan is the opposite over the adjacent. Okay, great. So SOHCAHTOA is great for angles between 0 and pi over 2. What about any other value of x? Who cares, yeah, right? But sine and cosine are well defined on all real numbers, not just for 0, between 0, the open segment between 0 and pi over 2. So how do we define sine and cosine in general? That's basically, I will just start from the end. SOHCAHTOA is not a definition. SOHCAHTOA is a theorem. Actually, I can't imagine how teaching SOHCAHTOA since the HOC2 girl goes in America today, to be honest.
Since the what?
HOC2 girl.
What's
You
that?
don't need to know about it.
You don't know HOC2? It's at least a financial news thing, you know, about the coin that she made, and many people lost millions of dollars.
He did lose millions of dollars.
Yeah, it doesn't
See,
exactly.
this is the part where not being part of the club is a good thing.
Not being a part of the world. I'm sorry, not knowing HOC2 girl. It's like
Is this a new thing?
No.
No, it's an old thing. It was like for 3 months ago. It was the topmost of it's a girl that got famous. You can look up for how she got famous, but she got really famous really fast, and then she sold a virtual coin and raised a lot of money, and then it dropped after 2 days, and now she's not famous anymore. But she is rich as far as I know.
It was almost 1 year ago.
Stop it.
1 year, wow. Okay. So actually, Octua Sohcahtoa is a theorem we will prove rather than a definition. Okay, we'll define sine and cosine differently, and then we'll prove a theorem that the ratios within a straight triangle are exactly as Sohcahtoa describes. Okay. So last chance. Does anyone remember how does one define sine and cosine? Yes.
I'm gonna take a guess at saying it's probably the circle, right? The circle.
It has
the
to do
unit
with the
circle.
Unit
circle, yeah.
circle with the triangle, and then you take the rotation around it.
Something like that.
Something
Yeah.
like that.
Without the triangle, but yeah. Okay.
Oh, without a
So
triangle inside?
if x is negative, so how could you?
Because the angle, you just call it a negative angle. You go backwards.
And
instead of
if
forward.
x is larger than pi over 2, and if x is
Well,
0,
because
And
that's
if
just
x
a
is
full
0.
revolution.
yeah, but it's not the triangle does not have the
If
okay.
X is zero,
That's,
then
I
the-
think
then
that's
the
the
line
main
is
thing.
straight.
The triangle does not have an angle.
Okay,
X.
sorry, my bad. Not the triangle, the line, the radius. The
Yeah,
radius
yeah,
from the
yeah,
center
that's
thing,
true. Yeah,
and the
that's true.
triangle that it makes.
No.
The
Without the
shape-
triangle, without the
Okay,
triangle.
okay.
There's no
Okay,
triangle
because the
here.
triangle,
Okay.
the thing I'm obsessing about is
It's
that
X and Y values.
the
at the point-
angles of the triangle has nothing to do with the x. That's the point.
Okay.
When you think of it as triangle, you always assume that the angle is x, but that's false.
Okay, so it's X and Y values at the point where it hits the circumference.
Yeah, exactly. Okay, exactly. So, for positive x, non-negative to be honest, for non-negative, I'll leave it as positive. For non-negative x's, if we travel along the unit circle, starting from 1, 0, counterclockwise, at distance of x, then we define the point we reached to be cosine of x, sine of x. I think one of the most surprising thing about the way I describe it is that I'm not mentioning an angle at all. I'm mentioning a distance because it's a geometrical definition. It says that we took an arc of the circle with length x. It's not exactly true because if we did full revolutions, then it's not an arc, it's a distance we've made, right? So that's the definition of cosine of x and sine of x when x is not negative. What happens if x is negative? Also, I'll write it Do you know what happens if x is negative for the story?
It's a negative of the
We're
sign.
going
No,
clockwise
it's the
instead
double
of
of the sign.
But why? That's not the definition. All right. If x is negative, we follow the same basic plot, but with a minor change.
Same negative.
But we travel clockwise, not counterclockwise. That's the whole difference. Okay, let's do some example. Oh, and one more thing, but we travel clockwise a distance of, we cannot go a distance of x because x is negative. So which distance do we take? Absolute value of x. Okay. So these are the two changes. So let's start with the positive value. Choose x being pi, right? And follow the story. Let's open GeoGebra.
Oh, you mean negative as
As minus pi.
Yeah, okay, so it's running at
Negative, that negative. Okay. So we chose pi. From which point do we always start? 1, 0. So that's starting point. And we travel a distance of pi. What's the distance of one full circle, the circumference of the unit circle? 2 pi. Remember that the circumference of the unit circle is 2 pi. Why is it 2 pi, by the way? By definition. We define, that's a choice. I think Euclid would have defined pi as the area, the circle, and then he would have to prove the circumference is 2 pi, which we need integrals for. And I'm going to define that pi is half of the circumference of the unit circle. But that means that I need to prove that the area is pi using integrals. I won't do that. That is done, well, usually no one does it. But if you look at my videos, I did it in because it drove me nuts. Because I tell you why. Because when if you ask, no, I won't, I will. Let's talk with the ChatGPT quickly. I never did that specifically on that. And how does one prove that the area of the unit circle is pi? I'll try to do it quickly and not too much.
reference secluded.
But one thing that is funny about it is that it's a circular proof usually. So he used the polar coordinates, Archimedes idea. SM. That's what Euclid does. Okay, this is here. Okay. Both proofs use the fact that sine of x over x goes to 1. We will prove that ourselves. Here it's done explicitly. He says, I'm using the fact that sine of x over x goes to 1. And by the way, I wrote it here on the fourth thing. That's that. I probably won't talk about it anymore, but all these proofs use that. I have a point here. So here, it's not mentioned directly, but it uses the fact that the derivative of sine is cosine, which uses sine over x goes to 1. Implicitly. How does one prove that? Look here. Within the proof, that's exactly what I was looking for. So I asked him, how do I prove that the area of the circle is pi? Are you with me so far? During the proof, he used the fact that sine x over x goes to 1. So I told him, how do you prove that? And during the proof, since the area of the full circle is pi, he uses the fact that the area is pi. Okay? That's just for my entertainment. Can't use the circular argument.
No.
Sorry for the pun. I wonder if he'll I wonder. Yeah. The user jokes about circular reasoning. You are absolutely right. And the very notion of length of an arc and the definition of pi. So then you use that geometry to prove sine of x over x and feed it back. You got it. That's pun intended. It's scary. GPT, his banter is even good.
UAE, they've announced that each citizen, they'll buy each citizen ChatGPT Plus.
Oh, really?
Yeah.
Yeah, they have money. Okay, I won't continue to argue with him, but I do like that he found the circular argument here. He said, when I'm proving sine of x over x, I use the geometry. When I prove the geometry, I use sine of x over x. So all I would say about it is it drove me nuts for years because that's the way teachers teach it in the university. And then I look for it, and there is a way to prove the area without using sine at all. The connection between the area and circumference. Okay. In any case, remember the circumference of the unit circle is 2 pi by definition. So for our course, pi by definition is half of the circumference of the unit circle. And now go back to the story, which you may have forgot, and I will remind you. We're starting at the point 1, 0, and we're walking a distance of pi. Since the whole circumference is 2 pi, then where do we get to? Half the circle, we get to this point. Agreed? So we get to -1, 0. And by definition, we define that point to be a cosine of pi, sine of pi. Second, sorry. The size is fine. By our very definition, we went counterclockwise a distance of pi, we got to that point. So our conclusion here is that what is cosine of pi?
It's -1.
-1. It's because the x value here, right? Examples. Therefore, cosine of pi is -1. And the sine of pi, what is that? 0. Okay, great. Question, yes, Sam.
So what is the shtick with degrees and radians then?
That's exactly that. That's a good
It
question.
seems like radians is what we originally used to define
Exactly.
cos and sine.
Exactly. Radians is the natural definition. Degrees is the human. If you were only compute, I don't know, but if the computers were ChatGPT, who knows? But degrees were a human invention just for us. For it, yeah.
How about stuff?
I will speak about it in remind me in a few. I just wish to go over the definitions, and then I will tell you about the difference between radians and degrees. Okay, let's do another example. Now choose x equals minus pi over 2. So it's a quarter of the circumference. And because of the minus, at which direction will we go? Clockwise, exactly. So we'll do a distance of pi over 2 clockwise. That's what the definition tells us. So if I do quarter of a circumference clockwise, I get to this point. This point is 0 minus 1. And by definition, the values here are cosine of minus pi over 2 that whole thing after the sine as well. Yay. Okay. So cosine of minus pi over 2, what does that equal?
No, 0.
0, that's the x value. And sine of minus pi over 2 is -1. And just make sure that's the sign we all know and love. And it's a bit confusing to do it on the same graph. So I'm deleting everything, but if I'll take I plot sine, I took 2 values of sine. I gave you example of 2 values. One of them, the second one, was minus pi over 2. What is the y value of sine here? -1, exactly what we said. And at pi, where x equals pi, it's, where is it? Can you see the numbers? It's just a bit to the right, because that's 3, and pi is 3, 1, 4. So here it is. And what's the value there?
0.
It's 0. And what did we find out? That sine of pi is 0. So the graph plotted here is exactly the sign that I defined for you guys.
It even looks like the sine graph you could like condense back into that circle, like through some sort of like transformation of space.
Yes, but it won't be condensed. I think one of the ways to do it looks as such. I will take a new one. To be honest, I don't really love it. Students love it. It's really blue. One brown does it, I think. But I don't like. I don't think it's helpful. But I'll show you
No, but
anyway.
it looks cool.
Yeah, that's the point here in this case. Right, something looks cool and some things looks cool and are helpful. This one is not too much. So I'll take any A that will be my x-axis and I plot the point with angle A. So the point would be cosine of A, sine of A. And I plot the y values of this point. Y equals sine of A. And now I'll plot sine of x. And I plot x equals A. And I will do this. Ooh. Right, that's what you usually see. See that if the angle, if you take the angle here to equal the distance here, then that is what you're seeing. Don't see it as smoothly as I. But when the angle here, the angle is equals to the distance, that means that the arc length is equal to the distance, then the y value of sine is exactly the y value of the unit circle. That's not surprising because it's just a geometrical motion picture of what I just told you by definition. I'll put it on the board as well, on the board anyway, because I already did it. And for cosine, it's the x value. Okay. Now, what's the deal? Seinfeld episode. What's the deal with degrees versus radians? And I'll show you the following question. That will show the main difference. Say you draw the sine function in degrees. And I'll give you a schematics of it. Mainly because if I draw it in GeoGebra, it will give you a huge hint to the answer to my question. So this is the sine function, and this is 90 degrees, and that's where the sine function gets to its top. That's 1, and it continues both direction. Now, I'm looking for the tangent line at x equals 0. What is the formula for the tangent line at x equals 0? What do you say? That's a high school level question. I draw the sine function and I ask you what is the formula or the tangent line at x equals 0. Anyone have any idea or guess?
Yeah.
What is it? Do you care to share with the class, Sammy?
Is it y equals x?
Okay, so Sammy suggests
Wait, hang on.
bravely
What's cos of pi?
that it's y equals x. Now explain to me, Sammy,
Oh, doesn't make sense.
why did you,
It's y equals minus x.
why? What
Did-
science do you do in order to say it's y equals x?
Because I differentiate sine.
Okay, the different, and I guess that's where you're stuck. The derivative of sine is cosine.
And then the derivative
Cosine
of
of
sine
0
at any point is
is 1. So it says the slope of the tangent is 1. It goes through the point 0, 0, so it must be x. You nearly had me convinced. Now let's look at the GeoGebra. I'll clear that here all. And okay. So here is the function sine. Do you agree 90 just does not show 90, sadly. Here it does. That's not. Oh, wait. Okay. So this is sine over 90. It exactly reaches its peak. And now I'm going to draw the function y equals x. How do you imagine it? Y equals x. Where is y equals x?
Somewhere.
It's the red line here. First of all, does that look like the tangent?
1 point.
No, it intersects with the function. It doesn't make it the tangent at one point. When we learn about derivatives, I will scold you for that remark. But 1 point is the tangent. I don't know which point, but okay. But that does not look what you imagine. Do you agree about that? But now let's draw, because the purple line isn't sine of x. It's sine in degrees, which is a stupid thing. Now let's draw sine of x, the real sine of x. That's that. And other than the scary prison vibes coming out of it, it is rather similar to y equals x. Do you agree?
1 point.
At one point or another. How I met your tangent. You should do something.
A weird love story where 2 people just met at 1 point and never again.
Yes. So I just hit home. It's the very same graph, just changed of perspective. Who do you see here? This I will copy with the formulas. So who do you see here? This function here, what is that? That's sine of x. And the red one, that's y equals x, which is actually the tangent, right? And the purple one, that sign in degrees. And why does it make sense? Because when does this sign reaches its peak? At 90. And we're here at 10. It's a long way ahead. The actual sign reaches its peak at half of pi, which is 1.5 something. Okay? Or it's 5.7 something. So where did Sammy go wrong? What was the mistake in the algebra behind the whole thing?
I was differentiating sine x rather than sine of 500.
Well, yeah, that's true, but the point is,
I didn't realize, you didn't
Obviously.
specify which one you were using.
no, I did specify. No, I
Okay,
did
so then I wasn't
specify.
listening.
No, it's not that you weren't listening. You made a mistake. And that's the point. You were derivating sine of x as you learn in high school, and you learn that the derivative is cosine of x. But point is, the derivative of sine of x equals cosine of x only when defined like we described, and that is called radians. The angle x measures the distance on the circumference or the arc length. An angle in radians is equal to the arc length. That's what radians mean. And it's an arc length when you didn't do a full revolution yet. If you went on full revolution, then it's a distance like I told you. Okay, but the idea in radians is the arc length. And only in this definition, the derivative is cosine of f. In order to describe a sine in degrees using the real definition of sine is, let's call it sine d, sine degrees, okay? And what's the definition of sine degrees? So you take the normal real sine and you just need to do some converting. If you know that you got degrees, then you need to divide by 180 and multiply by pi. That's the conversion rate, because a full circle is 360. Half a circle, you can think of it also as 2 pi over 360, if it helps. The same, right? That's the conversion rate, the ratio between the two methods. So, Sammy, I did not need to specify. That's like the real deal. And once I drew it in GeoGebra, I'm showing you, I'm revealing the trick behind the magic, right? But I'm saying that's the actual way to do it. And when I tell GeoGebra sine, he understands that I mean radians always, right? And that also gives the answer. So if you wish to derive that function, what's the derivative, excuse me, of sine in degrees?
2 over pi 360.
Yeah, it's 2 pi over 360 times cosine of cosine in degrees, basically. Let me just write that for short. Agreed?
But you still need the 2 pi over 360 inside.
Not because I wrote in degrees.
Oh, okay.
So it's the same thing. But in any case, therefore, the slope of the tangent is 2 pi over 360, which is pi over 180. It's driving me nuts. It's pi over 180. And now let's write y equals pi over 180 times x. Can you see that line? No, you cannot. It looks completely equal to the sine. It's also the same color, which is annoying. I'll change the colors just a second. Let's make it yellow. Now you can see it. So that's the sine, the purple one. That's the tangent, the yellow one, seems the same. And if I'll zoom out, I need to zoom as before. Setting, and the x goes from minus 180 to 180. And here you see the sine in degrees, sorry, and the actual tangent line to it, which is pi over 80x. And you would not have guessed it. I use the fact that you won't guess it to understand just how much radians are important. So in very short, if you believe, in short, if you believe that the derivative of sine of x is cosine of x, you already are using radians. It's only true in radians, it's not true in degrees at all. Okay, so that shows exactly how much radian is important. And I can tell you that it's more true, because maybe degrees are, I don't know, so-called true. But then you have to know that the derivative of sine is not cosine, it's pi over 180 of cosine. And I think we all agree that would be a horrible world to live in. Any questions so far?
Please go back up just a sec.
Sure.
When did we skip to derivatives?
So you're correct, but Sammy asked me about the difference between radian derivative, and it's radian degree, sorry. And it's true that in order to prove what I just said, we need to learn about derivatives, but we will do it. We will see this in this class. But I think it's the fastest way to explain what's the main difference between radians and degrees. And also, whoever did in high school, I'm not sure in different nations you come from, but in Israel, when you do trigonometry geometrically, you can use degrees. But when you do the calculus of trigonometry, you always use radians. And that's the reason, because you derive it. When you do geometry, you put degrees, the calculator fixes that for you, and you are never put to the test because you don't actually do anything with the actual function of sine. But in calculus, when you analyze the function, the graph of the function, you have to use radians. Otherwise, you get nonsense result that you just seen. Okay? And why is that true? And I will say, we will prove that later. Right? Not now, but we will prove that in that course. Maybe next lesson or the one after that. Any questions up until now? So now let's study some properties of the trigonometric functions, starting with SOHCAHTOA. First, given two triangles, that would be one with a right angle, and here x, and here x, and call this the hypotenuse C, the opposite A, and the adjacent B. And the second triangle is this one with the right angle with the angle x, and the hypotenuse will be large C, capital C, and capital A, and capital B. What can you say about these two triangles?
That's a similar triangle.
Right, they are similar triangles. These triangles are similar to one another. Therefore, what does it mean?
It means that they have
They have the same ratios.
The ratios of the edges are the same. Agreed?
I did this with the kid I was tutoring yesterday.
Oh. So.
I also got mixed up between similar triangles and congruent triangles.
Yeah. They're not
ChatGPT
congruent, they're similar.
corrected me, and I was like,
Yeah.
ah,
Yeah, they're similar, it's important. By the way, why similar triangles have the same ratios?
Their angles, their angles are the same, so
That's the definition of similar.
so the sine and cosine.
No, but
Wait,
that's
what's
not
the
a
question?
proof. That's
What's the
not a
question?
proof. That would be circular logic again, because now I wish to prove SOHCAHTOA. I can't use it, right?
You're trying to prove SOHCAHTOA.
Yeah.
what was the
So
question? Why they similar?
yeah, no, they're similar by definition. They have the same angles. They're similar. The theorem is that the last angle is equal because it's a triangle. That's not where I'm getting at. They're obviously similar. My question is, why do similar triangles have the same ratios between the edges? And Thomas wanted to prove that using sine and cosine, and I'm saying that would be circular because I wish to prove SOHCAHTOA. Okay, so the answer is there is a geometric proof that Euclid did in
interior
his
angles
book.
are the same.
It's very nice because I understood it. It's not that complicated at all. But there is a geometric proof to that claim. I don't remember which one it was, but whatever, I won't go over it anyway. So this has nothing to do with trigonometric function. But now, therefore, we can calculate the ratio of one such triangle, and it will equal them all, right? If you find the ratios of one triangle, then all other triangles have the same ratio because of similarity, not congruity.
I think there's quite a nice geometric proof to prove it.
Not an easy one. Yeah, it is easy, but not a known one. Not a known one.
I don't know if you take any two arbitrary lines
Yeah,
and then you draw a line like that,
yeah.
like across, and then you just move that line further and further and further back, you create multiple triangles, but all the interior angles are shared through
Yeah.
angle theory. And then
How do you calculate the ratio?
the ratio.
Because, no, because I'm asking, triangles are similar, therefore the ratio between the opposite and the hypotenuse is equal. How do you convince me of that? Say what you're saying will help me see it using a drawing, but it's not a geometric proof.
Okay.
But there is a nice geometric proof that Euclid did. I don't remember it, but I remember it was nice. I need to look it up, but not now. In any case, we need to calculate it for one triangle. Do you care to guess which triangle would I look at?
Triangle.
Right angle with angle X, but that's all of them. Which specific triangle with a right angle and an
The
angle
unit
X? A what?
The unit triangle.
So what's the unit when the hypotenuse is 1 within the unit circle? That's true. So look at the following. I'm going to the unit circle. Everything. Need the circle, I will need one text. I don't need the point and I don't need anything. Okay, I'll create my own point. Okay, so assume the angle is X. The point and cosine of pi over 3. Sine of pi over 3, that's the point. Segment OE, just we did, and segment and B and cosine of pi over 3, 0. Okay, look at that triangle. Just I should have named it, whatever. Segment O cosine of pi over 3, 0. Right? Let me get rid of all the H, G, I setting, label. No. Great. Okay, and now I can use the text. So that is let's get rid of the D as well. Okay. Okay. So I took a triangle with the angle X. So by definition, the point I've reached, the angle is the length of the arc. The point I've reached is cosine and sine. What does that tell us? What is the length of the hypotenuse?
1.
1, because it's the unit circle. It's the radius of the unit circle, right? What is the length of the opposite? What?
Pi in this case.
Yeah, but what is it? Sine of X, right? So that is
Oh, you're gonna prove.
exactly what I said I will, to be honest. Yes.
Wait, what did you say you're gonna prove? I thought-
Sokotoa.
Okay.
What is the length of the adjacent edge?
Cosine.
Cosine, right? So this is arguably, or I agree with this argument. So
Okay.
what's the word?
Obviously.
No, yeah, that's
Debatably.
but it's no, without debate. I agree completely that this is a specific triangle. Do you agree? It's not a general triangle, it's a specific triangle at a specific point in the specific place in the plane. Also, admittedly, I think that was the word I was looking for. Admittedly. Yeah. No, admittedly. I mean, I admit it.
No.
Yes, you're wrong. I'm right. In any case, the angle here is x, and these are the lengths of the edges. Agreed? Can one calculate the ratios of this specific triangle?
Yes.
Yes, it's not even that hard. It just they call division, right? So, so the opposite over the hypotenuse, what does that equal to?
I know.
Sine of x, that's the opposite over the hypotenuse. What is that? 1. So what? How much is sine of x over 1? Great, without the calculator even.
Division beyond the
Yeah. But you're allowed calculator, so it's fine.
Yeah.
A over age.
I don't know if I can recognize it on the page.
What's the adjacent over the hypotenuse? Cosine of x over 1. And what is that? Cosine of x. And what is the
Funny questions they can answer.
opposite over, and still going wrong? What is opposite over the hypotenuse? It's sine of x over
No.
cosine of x. Really? Well,
Yeah.
you are correct. I made a mistake. Opposite over the adjacent. So that's cosine of x. And what is the what do we define to be sine over cosine? That's the definition. Tangent of x.
That's
Tangent
great.
function of x. So that's the proof of SOHCAHTOA. Sine is O over H. Cosine is A over H. Tan is OA. So it's SOH, CAH, DOH. So I'll do it with colors.
I think we're too tired for this.
Oh,
Oh my god.
no, but it's not. If you read it like that, it's wow, but it's not. That's to read it as a certain order.
Thank.
You read it like Hebrew, so it's from the right to the left.
Yeah, I can change the.
You have to read
But in Hebrew, we don't teach it anyway.
You have to read it counterclockwise.
And then downward. Yes, okay.
Ah, it's a downward spiral. It makes sense.
Yeah. Like your life. Yes.
Exactly.
That I can.
Yeah, and then-
Why is CS?
Why is the C small and the T small? Do you write sign with capital S?
No,
Yeah.
I mean the highlight. Why is it like this T and
Oh,
the T?
agreed.
Over the-
Agreed. And I do not have any answer for that good question. Yes. In any case, oh, I know, but I know why. Because I didn't. That's the reason. Okay. In any case, that's proof of SOHCAHTOA. Why? Because again, for the last time, one might tell me, but you showed me that the ratio in this triangle is sine of x, cosine of x, tan of x. But because of similarity, for any triangle in the world with the angle x, right triangle with the angle x, the ratio must be the same as this specific one. And in this one, it's sine and cosine. So that's proof of SOHCAHTOA using the definition for sine and cosine using the unit circle. Any questions so far? And we get back to SOHCAHTOA. we understand that better. And so this is the basic of trigonometry. We didn't finish yet. I wish to show you some of the identities and tell you one identity, two identities that I won't prove, but you should know. And then we will do something one step beyond what we learn in high school in the way to derive sine and cosine, even though we didn't learn about derivatives yet, but we will prove some inequality that we will use later. I want to put all the geometric, trigonometric proofs together, and then we'll get back to calculus. So have a nice.
It's just calculus, isn't it?
So it's but
No,
isn't it
joking,
geometry?
joking.
No, but it is, have a good week.
I'm so tired.
Try to have a good week, a reasonable week. So thank
We
you.
have,
for
we
that.
have a, we have a quiz on Thursday, so.
A week that isn't all
Ah,
bad.
so it won't be good.
Yeah, what will be and what won't be on.
What won't